This is an HG camera, half gigapixel, built under the DARPA AWARE program by my group at Duke University. The camera has a spherical lens over here on the left, and then behind each of these ribbons connects to a 14 megapixel micro camera. So as a whole, the camera has 64 of those, and it puts out somewhere around half gigapixel per frame, and at 20 frames per second, somewhere around 10 gigapixels per second of data. This is the kind of thing you can do with optics, that we have a lot more information than any other sensor modality, and we can imagine getting to terapixels or petapixels of data coming from an optical system. But we're not going to be able to do that with coated apertures and obscurants. We need optics. And so today we start our discussion moving away from just simple obscurants and talking about refraction, diffraction, and interference as components in optical systems. Let's get started. Computational Imaging. Episode 25, Focal Imaging. This is the first time we talk about focal imaging in this course, but it certainly won't be the last. We're going to use lenses to form images. So let's understand what lenses do to the geometric rays that we've talked about in this chapter. First of all, as I'm sure you're all familiar with, if a bundle of rays comes in parallel to the axis of a lens, they're refracted by the lens to focus at a point at the back focal surface of the lens. On the other hand, if the rays go through the front focal surface at this point, then they're collimated by the lens to go out parallel. This is kind of the lenses work in reverse, the same as they do moving forward. The third rule is that rays that pass through the center of the lens are undeflected. This is based on the assumption that the rays are coming in normal to the same orientation to the surface on both sides of the lens. That's not technically true for a lot of lenses, and a lot of the ray rules that we're going through here are abstractions for ideal lenses. Then we get into real ray tracing, we'll get somewhat more complicated behavior. But if we use these three basic rules, we can understand the basic focusing mechanism of a lens. Here we apply our three ray tracing rules to find the image point for light emitted by an object point shown here. So here's our object point. One ray goes through the center of the lens. One ray comes in parallel to the optical axis and is refracted through the back focal point here, and then goes through the image point here. One ray goes through the front focal point here and is refracted parallel to the lens, and all those rays come together at an image point. Now we find the relationship between the image point and the object point, and the distances from the object to the lens d naught, and the distance from the lens to the image d sub I, by a little bit of geometric analysis. So this ray through the center forms a triangle with side length x naught here and side length d naught here, and then the similar triangle on the other side of the lens goes from the center of the lens, distance d sub I here and a height x sub I here. So we can say that x naught over d naught is minus xi over di, where we say that xi is negative if it's below the positive x-axis. Another set of similar triangles has this relationship. Here we consider height xi, and this distance here is d sub I minus f, and this is similar to this triangle with height x naught and distance f. The similar side on the lower half of the diagram has a height x sub I here, and then a distance f here, and a distance d naught over f here, and a height x naught here. So we have these three relationships between the various unknowns, x sub I, di, x naught, and d naught, and then we assume that f is a known. So one thing we might want to do would be to solve these equations to eliminate xi and x naught, and if we do that, we get the thin lens imaging law that 1 over d naught plus 1 over di is 1 over f. So this is a relationship. If you put an object a distance d naught from the lens, then that object will form an image at distance di behind the lens. Very well known, of course, law. And then similarly, there's the magnification of the system, where we saw already that x sub I over d sub I was equal to minus x naught over d naught. So the magnification of the system, it would be the height x sub I divided by the height x naught, is equal to minus di over d naught. Okay, so that's how lenses form images, and obviously they do something very magical compared to what we've seen with coated apertures, in the sense with the coated aperture, we measure one ray from an object point coming through a coated aperture, but here we can measure all the rays emitted by an object point coming together an image point, and this, as we saw with the coated aperture analysis, leads to a much higher angular resolution and much higher signal to noise in measuring the image. We will deal a lot with lenses throughout this course in optical elements, but we'll keep them in a very abstract form. This is not a course in lens design and ray tracing. This is a course in computational imaging system design, and so our understanding of lenses will be fairly abstract. Of course, real lenses don't work as simply as we've described here, and so there are computer programs available like Zmax and Code 5 that allow you to design real physical lenses and trace the rays through them and see how well those rays actually come to a focus. So this is geometric aberration, because there are approximations that we've made in the operation of refraction on three-dimensional surfaces that with real surfaces, lenses won't come quite to a focus and we'll get some blur. This particular image is generated using a Jupyter notebook that's available on the GitHub repository that goes with this set of lectures. And so it solves for each ray what happens to the refraction at various surfaces, and can go through and trace the rays and analyze real systems. When we look at ray tracing in practical systems, a lot of times we're interested in what happens to bundles of rays. We assume that at the edges of between a set of rays, that all the rays will behave similarly. So when we analyze a bundle, we'll typically work in terms of the marginal ray and the chief ray. So optical systems contain stops. These are the apertures that will play a major role in this course. In this case, we have the exit pupil, and lens system has an entrance pupil, which is defines the bundle of rays accepted by the system. And then it has an exit pupil that defines the bundle of rays coming to the image plane. A ray that goes through the center of a stop is called the chief ray, and a ray that hits the edge of a stop is called the marginal ray. So typically, the behavior of systems is understood first by tracing what happens to the chief ray and the marginal rays coming through a system. When we come to a focus or an image, the marginal ray is coming from the edge of the exit pupil to the focus, and so will come in at some angle as shown here, and the chief ray will come in through the center of the focal position. So this is our focal spot, and ideally this is a infinitely sharp, fine point. Later we'll find that wave diffraction will make it so that the actual optical field cannot be focused to an infinitely fine spot. But in our geometric approximation, we can look at what happens to the system as it goes away from the focus. So the core problem in computational imaging systems, as we've seen over and over again, is that the world is multidimensional, but that sensors and detectors are two-dimensional. So in the imaging system, we've just seen that a lens will form an image from a distance d naught to a distance d sub I. So it images a two-dimensional object plane to a two-dimensional image plane, but the real world is three-dimensional. So we'll be interested also in the depth of focus as we move away from the precise focal position. How badly will the image blur, and what will happen? Here we could say that the ray bundle extends to a distance c, where over some distance delta z, and then delta z times this angle theta would tell us what the extent of the ray bundle is. This angle theta is the numerical aperture. It turns out to be 1 over the f number. So the f number is the aperture extent divided by the focal length, and then the angle that we have from the marginal rays will be defined by the exit pupil, and so that is basically A, our aperture size, and so the numerical aperture of the system is going to be basically 1 over the f number. So as we think about the depth of focus, we see effects like this, that if we have a large f number here, like f32, then the image will be blurrier at the focus, as it turns out. but we'll have a more extended depth of field. Whereas if we go to a fast f number like f5.6, then the background is out of focus because it's at a range where well-focused images don't form. These are slides from John Grievenkamp's lecture series on geometrical optics, where several of the slides in this discussion today are drawn from. Here's another example from Professor Grievenkamp's work, showing again with a large f number, we have a deep depth of field, and a fine f number, or a small f number, we have a much narrower depth of field. And if we zoomed in here, you'd find that the resolution at the focus is actually somewhat higher with the small f number. Here's yet another example of various f numbers and shutter speeds for looking at objects. When we think about how we want to focus systems and how we want to analyze the depth of field, we get to this term of hyperfocal distance. So when we want to, typically, in a camera system, we'll often be looking at objects that are far away. And so as we look at objects far away, we have the analysis of the objects that are effectively infinitely far away, and then they come into focus at some focus position, and then we get to a near focal point. The near focal point would be where the focus reaches its point of maximal blur that's acceptable. So you could always choose to focus at infinity when you take a panoramic shot, but if you focus at infinity, then the focus will uniformly get worse as you move in toward the camera. So if you want to have maximal depth of field, you would choose instead to focus at some camera focus position, so that as you move to infinity, you get some blur that degrades the image, and then as you move toward the near point, you get some blur that degrades the image. But over this entire depth of field, the image blur is acceptable. So if you focus at infinity, you would have a very limited depth of field, but if you focus at this intermediate position, which is called the hyperfocal distance, then you have acceptable focus over some wider range. Here's how we can solve for the value of the hyperfocal distance. So we set z naught equal to the hyperfocal distance. Z sub I here is f plus c max f number. So f, if zi is equal to f, then z naught would be equal to 0, and we'd be focused in infinity. Now we want to have the blur at f be equal to c max. And so then delta z, the distance we are from the focal plane, is this c max f number. And so if we add that to f, that's our zi if we're focused at the hyperfocal distance. Now we can solve this equation for the hyperfocal distance, and we find the hyperfocal distance is roughly f squared divided by c max f number. So if f squared, if f was 100 millimeters, f squared would be 10 to the minus 2 meters squared, and then c is typically going to be something on the order of 2 pixels or so. So it could be like, let's say, 10 microns. So if f squared is 10 to the minus 2 and c max is 10 to the minus 5, then the hyperfocal distance would be around 1,000 meters. But we divide that by the f number, so it could get down to like 500 or 300 meters if we had f2 or f3. So that's kind of a range for what the hyperfocal distance will be. As we make f smaller, then the hyperfocal distance will get shorter very rapidly. For example, if we made f into 1 millimeter, f squared would be 10 to the minus 6. And so the hyperfocal distance could be well under a meter. It could be even just 10 centimeters or so. Okay, so this is a parameter that will be very useful to us in evaluating optical system design and performance, and we'll use occasionally simple geometric rules for as a first order analysis to understand how lens systems work. But in the future lectures, we're going to start by talking about a wave theory of lenses in the next series of lectures, and then eventually we'll get on to talking about what lenses do with partially coherent and incoherent fields. That's it for how optics work. Next time, we're going to wrap up our discussion of geometrical optics by talking about how ray imaging can be used to understand systems that use lenses. So even in a system that uses the lenses, oftentimes we understand, as you've seen with the ray tracing in this discussion, how the system works by tracing rays through the system. And so we can, as we saw already in this set of discussions, we can treat the rays through the center of a lens as projections for use for projection tomography. So we can do optical projection tomography. But these projections work in any kind of dimension, and computational imaging is about understanding hyperdimensional systems that are not just spatial. It can include spectra and time and polarization and radiance. And these systems can be understood as implementing the simple kinds of coated aperture projections that we've already talked about for coated aperture tomography in these lectures. This is a video that I find amazing every time I watch it. Here we're looking at the blink of an eye. So the image on the left is coated aperture data taken by a coated aperture over a space-time scene. And the video on the right showing an eye blinking and the glint in the eye as the system opens up. Those 148 frames on the right are reconstructed from the single frame on the left using coated aperture tomography, the same as we've talked about, except implementing it over a space-time field instead of over a purely spatial three-dimensional volume. We'll talk about how that works in our next episode.